Our home, planet Earth, is one of 9 or perhaps only 8 planets that orbit the Sun. They were formed 4.5 billion years ago in a solar nebula. The great principle of this lecture, the 36th in our series, is that Earth, formed by gravitational attraction of dust and gas, and then differentiated into core and mantle and crust. In this lecture, we shift our focus from the varied objects of the solar system to our home planet, Earth. But first, I'm going to finish with our travelogue, a travelogue of all those different solar system objects. After a quick review of the last lecture, I'm going to introduce the enigmatic objects that lie beyond the gas giant planets, Pluto, the Kuiper Belt objects, comets, as well as the hot new science of extrasolar planets. The second half of this lecture then will introduce planet Earth in terms of its violent origins and its interlayered structure of core, mantle, and crust. Recall that the planets are divided into 2 groups of 4. We have the 4 inner terrestrial planets, Mercury, Venus, Earth, and Mars. These are rocky planets, small, dense objects, each with a distinct characteristic. And then the 4 gas giant planets, planets that are composed primarily of hydrogen and helium with swirling atmospheres, much farther out from the Sun. The differences between these inner and outer planets was the result of the Sun's radiant energy. When the Sun ignited 4.5 billion years ago, the solar wind and the heat energy pushed the hydrogen and helium away, swept it out to the outer regions where it could condense as the gas giant planets, leaving rocky inner planets. In a sense, then, the solar system illustrates the process of chemical distillation. The higher temperature materials in the hotter end, the cooler materials farther out. Now, the solar system doesn't end with the gas giant planets. We have a number of additional, rather enigmatic objects that litter space beyond. And the first of those is Pluto, the 9th planet, or at least it is the 9th planet for a time more, and that may change soon, as we'll see. This is an enigma, Pluto. American astronomer Percival Lowell suspected the existence of this 9th planet from slight perturbations in Neptune's orbit. Recall that Lowell is best remembered for his maps of the so-called canals of Mars. Well, he called the missing object, the missing planet, Planet X, and he searched futilely for it until his death in 1916. The search was resumed by American astronomer Clyde W. Tombaugh, who painstakingly compared photographic plates of the night sky taken several months apart. He was looking for an object that moved relative to the fixed backdrop of the stars. Well, Pluto was discovered by Tombaugh on February 18th, 1930, from this photographic survey. Pluto is unlike any of the other planets we've talked about, and in several respects. First of all, it's quite small. It has a radius of only 1,140 kilometers. That's only 2/3 the size of the Moon. Though small, like a terrestrial planet, it seems to have a composition that's really a mix that's about half rock and half ice. So in that case, it's also different from the Jovian planets and the terrestrial planets. Pluto has an extremely elliptical orbit. It averages about 40 times the Earth-Sun distance during a 249-year orbit around the Sun. And yet, at some times, for about 20 years out of that orbit, it's actually inside the orbit of Neptune. Indeed, from 1979 to 1999, Pluto was the 8th most distant, not the 9th most distant planet. Well, there's going to be a vote pretty soon by the International Astronomical Union, and astronomers are going to vote whether to cast out Pluto from that list of planets. They may just make it another minor body that orbits the Sun far away. So the status of Pluto and all the things we've learned about 9 planets may have to be changed slightly. In any case, Pluto's orbit is significantly tilted to the plane of other planets. This is another thing that makes it odd, and it points to a possible origin of this planet or object of whatever it is. These characters have led some astronomers to suspect that Pluto is in fact an escaped moon of Neptune. Now, think about how this might have happened. If you had a collision, for example, with a comet or a large asteroid or some other object, it might have pulled that object right away from Neptune, swept it into its own orbit, which then is the current orbit of Pluto. Pluto is in effect a double planet, and this leads credence to this idea. Its moon Charon is only about half its size and in a very close orbit. Again, this behavior is quite different from any other planet. Well, on beyond Pluto now, to the Kuiper Belt. The Kuiper Belt, which contains hundreds of objects up to a few hundred kilometers in diameter. From the darkness of the surface of these objects, they appear to be at least partly rocky. They've done spectroscopic surveys of the Kuiper Belt objects. You look at the light coming to us that's reflected off the surface, and it appears that there are two different populations of these objects. Some objects, the light reflecting off has more red wavelengths, the reddish Kuiper Belt objects. Others are slightly bluish. You have the more blue-type Kuiper Belt objects. And this suggests that there are at least two different surfaces, perhaps two different compositions of objects. It's hard to know exactly what these different compositions are. Maybe some are more icy, maybe some are more rocky. We don't know. Some scientists have suggested that Pluto is in fact the largest of these Kuiper Belt objects. Again, we just don't know. They're too far away and we need more studies of these distant objects. And then we come even farther away to comets, the most distant objects known that are gravitationally tied to the sun. These have extremely elliptical orbits, with an average distance about 50,000 times the Earth-Sun separation. That's 3/4 of a light year. Dutch astronomer Jan Oort, who lived from 1900 to 1992, suggested that a large number of comet-like objects occupy a distant band called the Oort cloud. These would be primarily frozen liquids and gases, clumps of this material, far out in space. And once in a while, some of this material is jostled and starts its long journey inward toward the sun. So these comets that are occasionally jostled free start an orbit that sometimes takes millions of years to complete from deep space. Of course, when a comet gets close to the sun, that's when the tail forms. That's when the volatiles, the methane and the water ice and other materials start vaporizing and the long tail forms, and that's when we see the comet in its spectacular glory as it approaches the sun. If the orbit's further perturbed, for example, by Jupiter or another large planet, the comet can adopt a much shorter orbit closer to the sun. Comet Halley, for example, is an example. It has a period of about 75 years. So it's a much shorter orbit. Once in a while, we see other interactions with comets. You may recall in 1994, in mid-July, the collision of comet Shoemaker-Levy with Jupiter, a spectacular event. First, Jupiter broke that comet into 20 separate chunks, each huge, each more than a kilometer across. And each of those chunks successively hit the surface of Jupiter, causing an immense collision, stirring up the inner gases from Jupiter, swelling and swirling the atmosphere. So we were able to study the composition of the deep atmosphere of Jupiter. We were able to measure the intensity of these incredible impacts that release the energy of many hydrogen bombs. There's actually an intriguing controversy now about small comets which may be pelting the Earth all the time. According to astronomer Louis Frank of the University of Iowa, such comets constantly bombard the Earth, perhaps as many as 10 impacts every minute on the Earth. Now, these are supposed to be small comets, just maybe the size of a house, light, fluffy things that hit the atmosphere and dissipate. This is all based on satellite measurements, which show local variations in ultraviolet radiation in the upper atmosphere of the Earth. That's how these comets have been identified. Over time, Frank says, these comets contribute significantly to the total amount of water on the planet. Well, other scientists disagree with this intently. They say that Frank's data are flawed. They say that all he's seeing is instrumental noise. And this is the kind of argument that goes on all the time in science. They argue that if such comets were common, then the surface of the moon also would have to be bombarded. And how could the surface of the moon be bone dry as it is? There's absolutely no water on the surface of the moon. These debates have, by the way, turned quite nasty at times, and each side claims that the other side is closed-minded. But eventually data is going to win out, and we'll know the truth. However that debate turns out, we still have a huge amount to learn about these distant objects in the solar system. Now, before turning to Earth, let's examine one other hot area of planetary research. That's the search for extrasolar planets. Powerful telescopes provide opportunities for the very first time to detect the presence of these planets orbiting around nearby stars, stars that are less than 100 light years away. One of the techniques is to look for a slight, regular wobble that's caused by the interaction of the star with the large planet. When they orbit around a common center, that means the star has to be moving slightly in synchronicity with the orbit of the planet. The Sun, for example, it wobbles slightly in unison with Jupiter's orbit. And so you could detect the presence of Jupiter just by carefully measuring the position of the Sun. So far, more than a dozen planets the size of Jupiter or larger have been detected in this way by looking at the wobble of distant stars. And more of these planets are being found all the time, every month. This is a very hot area of research. Of course, ultimately, we'd like to be able to image extrasolar planets. And there's a new generation of space telescopes that are in the planning stage that can do just that. These are the great interferometric telescopes, the telescopes with two mirrors widely spaced, as much as 100 meters apart, orbiting around the Earth and focused on nearby stars. Such telescopes may be able to resolve individual Earth-sized planets. What's more, it's possible that these telescopes could resolve the spectrum from oxygen. Remember, each element has its own characteristic spectrum, hydrogen and helium and so forth. Well, so does oxygen. And you might actually be able to see the absorption bands of oxygen in the atmosphere of an Earth-like planet. If we saw oxygen, that would be a clear sign of life. Because oxygen is such an unstable element, it has to be replenished by living things all the time. We're now going to shift gears. For the second half of this lecture, as well as the next 6 lectures, I want to focus on our own dynamic planet, planet Earth. Earth is in many respects like the other planets of the solar system. It orbits in the same plane and in the same direction. It formed at the same time about 4.5 billion years ago. It's composed of the same chemical elements, and of course, it obeys the same natural laws, the same physical laws of motion, of energy, of electricity and magnetism. But the Earth is also unique. It has extensive surface deposits of liquid water, which is the essential medium for life as we know it. Now, it's true that Mars may have had surface water at some time, but it doesn't now. And Europa may have a subsurface ocean, but it's doubtful it ever had a surface ocean. So Earth is unique for our time right now. Many of the characteristics of Earth also seem well suited to life, to a habitable surface. For instance, Earth is about 150 million kilometers from the Sun. That's close enough to maintain liquid water, but not so close as to boil it away. The 24-hour rotation period, that's short enough to prevent extreme temperatures between night and day, but it's slow enough to prevent extremely violent weather patterns that could disrupt the surface. Then the Earth, it has a radius of 7,000 kilometers. That's large enough so that the fast-moving water molecules can't evaporate off the planet and escape into space, as they have done on Mars, which is somewhat smaller. So here we have a planet that has the ideal distance, it has an ideal rotation rate, it has an ideal size, it has liquid water, all characteristics that may be essential for life as we know it. I want to turn our attention to Earth's earliest period, the period called the Great Bombardment, when the Earth was accreting in its final stages. A proto-Earth had formed, a sphere which is almost the size of the present-day Earth. But that sphere was molten, it was chaotic, it was a place of hellish violence, because you had constant raining down of asteroids and comets blasting the surface. You had volcanoes spewing molten lava and gases in great clouds and billowing fountains of red-hot molten rock onto the surface. This was an amazing place to have seen. This place would have really been astonishing. Wouldn't have been easy to survive there, though, I must say. Well, as that bombardment subsided, the red-hot molten sphere slowly cooled. A black crust appeared, the first rocks. And although that crust was constantly broken by volcanic activity, you gradually had areas of land forming. You gradually had an atmosphere forming from the volcanic gases that came from the inside. You soon had clouds forming, atmosphere, the first rains, the first oceans would form on the surface. And eventually, as the surface cooled, we began to see an arrangement of oceans and land, something analogous to what we see today. A late-stage impact probably formed the moon. That was that great impact event where the Mars-like object hit the Earth and ripped out a chunk of the mantle and formed the moon. And then you sort of had to start that process of forming the ocean and the atmosphere over again. But eventually things settled down. So you have a sphere of molten rock, and what happens in that sphere? You get the process called differentiation, a separation of different materials deep inside the Earth by gravity, by density. This process has given the Earth a radial structure, a structure not unlike the layers of an onion. Now, the densest material was primarily metals, iron metal, very dense iron metal, and nickel metal, which joined it. Also, probably most of the gold and the silver, the uranium, the lead, many other elements which would have sunk down in that dense metallic center. Ultimately, we formed a metal core. That metal core increased in size until it was a sphere at the center of the Earth, about 3,470 kilometers in radius. Now, the dense core represents only 17% of the Earth's volume, but fully a third, 33% of its mass, because it's so dense. Now, by contrast, the lightest material, including many elements such as sodium and potassium, aluminum, hydrogen, lithium, these elements don't form dense minerals at all, and so they basically float up to the surface. They concentrate in a relatively thin surface layer called the crust. And that crust is typically less than a few tens of kilometers thick. That's where we live. That's where all the action that we see is, a very, very tiny fraction of the Earth's volume indeed. The remaining material, that's about 80% of the volume of the Earth, and more or less 2/3 of the mass of the Earth formed the Earth's mantle. And the mantle is composed primarily of elements oxygen, silicon, magnesium, and iron. Almost 98% of the mantle is just those four elements: oxygen, magnesium, silicon, and iron. And of these four, oxygen is by far the most abundant. So most of the different minerals deep inside the Earth and the mantle are oxides. Oxides of silicon, oxides of magnesium, oxides of iron. We know about the Earth's inner structure from the study of seismology. Seismology is the study of the Earth's inner structure using sound waves, and it provides our clearest picture by far of the Earth's deep interior. Now, sound waves pass through the Earth at speeds typically of a few kilometers per second. Different materials have different speeds. For example, speed is much faster if you have a dense, cold material, a solid material like rocks near the surface. And that speed decreases if the material is less dense. It also decreases if it's hotter, or even if it's partially molten, speed slows down quite a bit, but typically a few kilometers per second. Now, these waves also bend. As the waves pass through the Earth, they tend to bend as they go through materials of different density, partially molten materials, and so forth. In addition, these seismic waves, these waves of sound, bounce off different layers of the Earth. For example, at the core mantle boundary, much of the seismic energy, much of these waves bounce off and reflect back up towards the surface. We have two different kinds of waves in seismology. First, we have primary, or P waves. These are compressional waves. Now, recall from the earlier lectures that these waves, the motion of the wave is the same as the motion of the atoms. If you have a material and you push on it suddenly, then each atom tends to push on the atom next to it, and a wave of energy passes through the material as atom pushes against atom pushes against atom. That's the compressional wave, a primary wave, or a P wave, as it's called in seismology. You also have secondary waves, S waves. These are somewhat slower, and they're also known as shear waves. These are the waves that when you move an atom up and down, it jostles an atom up and down next to it. This is sort of like the wave. When you do a wave in the stadium, one person stands up and then the person next to him stands up, and you see a wave moving around the stadium, even though the motion of the individual people is up and down. That's a shear wave, also a secondary wave, or an S wave in seismology. Now, P waves always travel faster than S waves. And another important distinction, S waves quickly die out in a liquid. So if you have a liquid region anywhere inside the Earth, the P waves travel right through it, the S waves stop. Most of these seismic waves, most of these sound waves in the Earth are generated by earthquakes. That's a situation where rocks suddenly crack and break and suddenly move, and they generate a big pulse of sound and energy that goes swinging through the planet in various paths. You can also set off local explosions. And at least for local seismic studies where you're trying to study the detailed structure of a very small volume of rock, the best way to do it is set off small explosive charges at the surface, and that also provides sound waves for seismology. For this reason, because you can set off explosions and detect them, seismology has been greatly advanced because it's the key to nuclear test ban treaties. You can't have a nuclear test ban treaty unless you actually have a seismic network to look for those explosions. And so the U.S. government and the Department of Defense has put a huge amount of money into seismology, which of course makes the seismologists studying the Earth's deep interior very happy. By the way, seismic waves are measured by instruments called seismometers. These are just sensitive to very slight variations of ground movement. They usually involve a heavy weight sitting on a delicate spring, so the slightest movement on the ground causes the arm to move, causes a pen to jiggle on a paper. And I bet you've seen pictures of a seismic chart just before and after an earthquake where you have a little delicate squiggle and then a violent squiggle coming when the earthquake passes. That's simply due to the way that the lever arm moves as the ground moves. Seismology reveals the details of the Earth's deep interior, and it shows that the core is divided into two separate layers. We have a solid iron inner core, radius 1,200 kilometers. That's the centermost part of the Earth, and the maximum pressures at that core approach 3.5 million atmospheres, 5,000 degrees centigrade or greater temperatures. Then we have an outer core, which is liquid. Remember, S waves don't pass through liquid, so that's how we know it's a liquid outer core. It's formed primarily of a nickel-iron metal, but it has to have a small amount of some lighter element because the density of that outer core is not quite great enough to just be nickel-iron. Indeed, the composition of this outer core is one of those as yet unanswered questions that allows scientists to pose highly speculative models. It's one of the great fun things in science when you don't know something and you can just make guesses and sort of see how those models test out. Another one of the great debates and mysteries in science is the origin of the Earth's magnetic field, which probably takes place in that outer core, in the liquid core, as currents and as fluids circulate around deep within the Earth. This sets up a magnetic dynamo, if you will, sets up electric fields and sets up magnetic fields, which then are reflected in the north and the south pole of the Earth. The core mantle boundary, it's a fascinating zone for seismologists. Indeed, it may be one of the most complex and fascinating of all those inner zones. We see scattering of seismic waves at the core mantle boundary, which is quite chaotic and suggests that there might be huge mountains of dense material sort of sitting on this metal rock interface, which is the core mantle boundary deep under our feet. There may in fact be giant mountains 100 kilometers tall of dense minerals which are sitting on the very base of the mantle, and then lighter minerals surround it. It's a neat idea, and seismology is the one way we're going to be able to find out if that's true. Now to the Earth's mantle, by far the largest volume of the Earth. It's divided into 3 layers, each which is bounded by a seismic discontinuity. The lower mantle extends from about 700 kilometers down to almost 3,000 kilometers deep, and it contains more than half the Earth's volume. Now, in spite of the fact that the mantle is composed of what we call solid rock, it's actually an extremely dynamic region, which, as we see, drives most of the geology at the Earth's surface, because at those high temperatures and pressures, the rock becomes plastic, like taffy. It actually, over millions of years, moves and flows and changes, and that drives many of the activities at the surface of the Earth. Between 400 kilometers and 670 kilometers deep is the Earth's transition zone, the transition zone of the mantle. This is a region distinguished by dramatic phase transitions. You see seismic velocities increasing tremendously from the top to the bottom of the transition zone, and that corresponds to denser and denser mineral combinations as atoms rearrange and reform themselves into these denser minerals by phase transformations. Then we have the upper mantle, the upper 400 kilometers of the Earth, which features relatively simple composition of the entire mantle, that is, oxygen, magnesium, silicon, and iron, but in minerals that are very similar to the low-density minerals at the Earth's surface, the same crystal structures that you see at the surface. While seismology coupled with field studies and deep drilling then reveals that the Earth's crust is an extremely heterogeneous place, a much more complex place than the core or the mantle, or at least so we think. If you look at the crust, you see that it's compositionally varied. In some places it's volcanic rock, like the basalt lavas that pour out of Hawaii's great volcanoes. In other places, we find miles and miles of thickness of sediments of various kinds, sands and silts, muds, sometimes limestones, layer upon layer. And these are very different in composition from the basalts. The crust also has an extremely complex structure. It has faults and folds. It has mountains and valleys, earthquakes, volcanoes. And that will be the subject of the next lecture, as we'll see. To summarize in this lecture, we've seen that many mysterious objects lie beyond the 8 major planets of our solar system. We have the small, strange world of Pluto. That may be the outermost planet, or it may be the largest of the Kuiper Belt objects that lie far outside the orbit of gas giant planets, or indeed, it may be something quite different indeed. We just don't know. Even farther out, beyond the Kuiper Belt, lies the Oort cloud, the place where comets are spawned, where comets begin their epic journey from 3/4 of a light year away to gradually fall toward the sun, eventually to show their blazing tails in the night sky. And we are now beginning to see evidence from many planets that orbit distant stars. We see extrasolar planets and hint at other planetary systems like our own. At times we see giant planets that make other stars wobble. At other times we may actually see evidence of the planets themselves in telescopes which are now under invention. Our home planet then, it formed in a solar nebula of dust and gas. And as the Earth formed, it differentiated. The molten Earth separated into layers. The inner the iron metallic core with some nickel, an inner core that's solid, the outer core, which is liquid, molten nickel and iron. Then the Earth's mantle separated into 3 layers, the lower mantle, the transition zone, and the upper mantle, all composed primarily of just 4 elements, oxygen, magnesium, silicon, and iron. And then the crust, the dynamic, the varied, the heterogeneous crust, which we'll study more in the lectures on geology to come. But in the next lecture, I'm going to focus on the fact that the Earth remains an extremely dynamic planet.